What happens when our energy is negative? Our velocity faster than the speed of light, and time not only negative, but imaginary? Well, yes, all of those, yes, we'll get over all of these and more, believe it or not, in this video, but first, let's start the warm-up and ask a question of, why does math break physics? Okay, the process is simple, but I'd really like you to understand how we're able to break physics using math, and for that we'll use a light bulb. This light bulb. When we turn it on, it emits photons, or in other words, light. More photons, brighter light bulb. Less photons, lower brightness. Simple. We can represent the amount of photons emitted with a number, so this would basically be 1, this would be 7, this would be half, this would be 100, and so on. Now what we've done is we just abstracted a real physical thing into this number. A big word because it's kind of important for the whole process. Why is abstracting it important? Well, it's because now there's a number, we can do all sorts of things, like not only setting it to normal stuff like 1 or 0.5, but wacky values like 0, which gives us no emission, or -3. What would -3 mean? Well, for Blender it's simple, just darkness. A light bulb so dark it's sucking up all the light around it, but for real life, it doesn't make sense. And that's the point I'd really like to accent in this case. If this value is the abstraction of the amount of photons an object is emitting, then negative value wouldn't mean the object sucking in photons, or the object emitting anti-photons. No, this means the object emitting normal, ordinary photons, but a negative amount of them. That's the problem with abstracting. I always like to visualize it like this. You have a problem with a high level of complexity. If you abstract it, you reduce the complexity and the accuracy. So relativistic quantum mechanics can be abstracted into chemistry, chemistry into biochemistry, which can be further abstracted into biology, medicine, and so on. The general rule being that you can abstract things in different ways. So for a light bulb, for example, we can represent the brightness using the amount of photons, the energy of photons, and the... Okay, well, for photons that's kind of it. But my point is, this isn't just a straight line, it's a cone. A cone in which the further you go, the more blurry things become, and you can only go forward. You have the starting theory, which is currently mostly relativistic quantum mechanics, and then you just move on, never going back. Based on relativistic quantum mechanics, you can create chemistry, but based on chemistry, you can't create relativistic quantum mechanics. Based on biology, you can't create medicine, but based on medicine, you can't create biology, and so on. That's not to say that you can't use the evidence from further down to support the start, only that cells dictate how the lungs should behave, not the other way. And that's what abstraction is all about. But this video, I don't just want to talk about this deep, meaningful topics, because that's cringe. In this video, I'd like to have fun. So let's have fun and do some wacky math for even wackier physics. So first, let's start simple, with something nice and easy, not too complex. How about relativity? Time dilation, to be exact. Here's an equation. What does it mean? It means that we have a cube, number 1, moving forward, and a cube number 2 observing it, then this would be the time of our observer cube, and this would be the time of our moving cube. Now, if our moving cube is traveling forward at 1 meter per second, let's take a look at what happens after 1 second passed for our observer cube. Okay, not surprising, we moved by 1 meter, I mean, that's to be expected. What's the big deal? Well, the big deal is that if we insert our velocity into our equation, we get that whilst it was 1 second for our observer cube, it was 1.000000000000000000001 seconds, which is higher. Or in other words, time is relative. Time for our cube number 1 is different than time of cube number 2. Now what's interesting in this case is that we could switch them around. That's actually kind of the whole point of relativity. If we establish the moving cube as stationary, that's the relativity moment, then it's staying still and the entire world is moving away. So both of these cubes would perceive their own time as normal, 1 second per second, and the others as higher, 1.16 zeros and 1 per second. But how could both of these cubes perceive their own time as normal and the other one as higher? This doesn't make any sense. That's kind of like having 2 elevators in which the first one is higher than the second one, and the second one is higher than the first one. Except, like, that's a contradiction, right? Well, not quite, and here's where the genius of relativity really shines through. Imagine if we take our elevators and we tilt them at an angle. Now if we move them up, let's see what happens from the perspective of the first elevator. From our green elevator, we'll perceive the red one as being lower. From our red elevator, however, we'll perceive the green one as being lower. The concept of height is different for each elevator, and for an outside observer looking at them in the middle, they would be both at the same height. For relativity is the same thing, except in this case the height would be analogous to time and the slope would be analogous to velocity. I'll make a full video about general relativity soon, just give me like a week or two, maybe 3 or maybe a month. That by itself is already weird enough, but we can go further, because what if we're traveling at the speed of light? Well, physics tells us that you can't really, but we're here to break physics using math. So what happens if our cube, instead of moving 1 meter per second, moves at the speed of light? Well, first let's see what happens when the speed of our cube goes up. Right here I've graphed it in Desmos and we can see that as the velocity of our cube goes up, so does the time dilation. And at the speed of light, well, if we plug in the speed of light into our equation, right here we get c squared by c squared, which is 1, and then 1 minus 1 is 0, and square root of 0 is 0, so and 1 divided by 0, that's kind of infinity, which I mean it tracks. Alright, you may say something like, make it, but how could the time dilation be equal to infinity? This doesn't make any sense! But if you think that 1 second passing for a cube means an infinite amount of time passing for the other cube is weird, then... Okay, I just realized how unclear this point is actually, so I guess I should explain what actually, a time dilation of infinity would theoretically mean. It means that if we have a cube, which is staying still, and a photon that's just flying by, for 1 second, from the perspective of the cube, right, this photon travels like 300 million meters, right? That's fine. But from the perspective of the photon, this wasn't really a 1 second. From the perspective of the photon, for each 1 second that passes for a static still cube, an infinite amount of time passed. So the time is like frozen. No time is passing from the perspective of our photon, which, yes, is really, really weird, really bizarre, and kind of breaks the whole concept of time for us, but you're traveling at the speed of light, you're breaking physics anyway. But if you think that 1 second passing for a cube means an infinite amount of time passing for the other cube is weird, then just wait until you find out what happens when you go faster than the speed of light. Now that's a hard rule, right? The universe speed limit, and physicists would be disappointed with me trying to accelerate the cube beyond that, but we're not here to do physics, we're here to do math, and thus let's plug in speed of light plus 1 into our equation. Well, what we get is this, and once we solve it step by step, so right here c squared plus 2c plus 1, then c squared and c squared can't each other out, then we can call this y, because why would you care about this number? It's irrelevant, the only thing that matters is that it's a positive real number, and then 2 ones that cancel each other out, and then we end up with this, an imaginary number y? And because of how imaginary numbers work, we can just bring it up with a negative, and if our cube is traveling faster than the speed of light, for each second it perceives, the other cube gets a negative imaginary amount of time. Or in other words, if you will accelerate an object to faster than the speed of light, it... Nope, I don't even know how to describe it. Like, technically you achieved kind of time travel, I suppose, because the time is moving backward, except it's moving backwards in the imaginary axis, not the real one. So what would an object like this even look like? Well, no idea. No idea what imaginary time even is. So in case any of you ever wanted time travel, I've got something even more ambitious for you. Breaking time as we know it. Clearly we went too far. We broke physics too much, alright? There's a reason why you shouldn't really accelerate things past the speed of light. So let's do something simpler, like negative energy. And how convenient, I just happen to have made an entire video about energy, so it's about time that we break them. Let's pick a couple fun ones, like the radiant, gravitational potential, and kinetic. So first, radiant. What is radiant energy? Radiant energy can be described using the equation of E is equal to hc divided by lambda. So negative energy in this case would mean either first, us living in a different universe where Planck's constant would be negative, second, speed of light being negative, or third, wavelength being negative. First one was kind of boring. I mean, it just means redefining energy to negative and nothing changing. The second, however, is a bit more fun, because what would negative velocity even look like? Well, it means that an object is either going a negative distance forward or going back in time. Now, mind you that negative distance does not mean backwards, no, it means forward, just a negative number of meters. If you go 1 meter backwards, that's still just 1 meter, just in a different direction. So going negative meters forward is not as easy as you think. Okay, what about time? Well, time would mean just traveling back in time, which, funny enough, if you turn around, you get that you would need a negative amount of energy to travel back in time. Mathematically, of course, not physically. And then the last and most shocking thing, which is wavelength, and that's because negative wavelength could be the same as the positive, depending on how you look at it. Wavelength is just the distance between two things on the wave, two peaks, two zeros, whatever. Now, if you think about it physically, it doesn't make much sense. That's because, once again, what would negative distance be? Same thing as with meters, but mathematically, we do have an equation for cosine based on the wavelength, which looks like this, and we can plug a negative number. It's the same as the positive. So photons could actually have negative radiant energy. But that's boring. Next we have something cooler, potential gravitational energy, with the equation of U is equal to negative gmm divided by r. And what's really interesting in this case is that this energy already is negative. It has a minus. Gravitational constant is positive, mass is obviously positive, mass is positive, displacement is positive, which means that if you multiply all of these positive values, you get a positive value. Multiply that by a negative and you get a negative value. So how could that possibly make any sense? Well, just as I mentioned in my energies video, energies are a bit of a fiction and an abstract concept. So energy being negative in this case doesn't actually break anything. You just set your level for 0 and then it's going up or down. A good example of how it works would be a ball with a ground beneath it. Now, if we let this ball fall, it will go down. That's because its gravitational potential energy just got turned to kinetic energy. And once it falls all the way down, it has no more energy to give. So right here, its gravitational potential energy would be equal to something like 1, for example, and right here, it would be equal to 0. But this presents a problem, because what if we dig a hole and the ball falls even lower? If this energy is 1 and this energy is 0, what's this? Negative 1? Well, yeah, gravitational potential energy can exist as a negative number because you set its ground level. Ground level is 0, anything else is relative. And then you only care about the change in energy, not the total. So when we dig the trench and we get the ball to fall down even lower, whilst this energy would technically fall below 0, we don't care. It's more about how much energy we extracted from the ball, in this case 0 and negative 5, or 5 and 0, or 70 and 65, it doesn't matter, it's just about the difference. But don't worry, there's still a way for us to break it, and that stems from the fact that gravitational potential is a tool for describing gravity, rather than gravity itself. And that's because right here we have the distance between them, and so we see that if we stamp the ball right here and we let it fall, we're extracting more and more energy. But something really interesting happens as we let it go on, and that's because r is getting smaller and smaller and eventually approaching 0. And as it gets this close to the center of mass of our body, we get an equation which looks like this. As considering how we're going from the positive, this would basically mean that if we let our ball fall into the center of mass, we can get an infinite amount of energy out of it. It doesn't even matter how far we let it fall from. It's the fact that it goes to 0, not the distance itself, which gives us an infinite amount of energy. What? Why are we doing it then? Why didn't we already dig a hole into the earth and drop a ball? I mean, an infinite amount of energy, that's more than our solar system, or our galaxy, or possibly the universe. Just dig a hole, drop a ball, and all our problems are solved, right? Well, not quite. That's because here we once again broke physics using math, and we abstracted gravity into this nice equation, which simplified it a bit, but also lowered the accuracy. And that's because in order for a ball to fall into the center of the earth, there would have to be nothing in the way. But if there is nothing in the way, then what would be attracting it gravitationally? Instead of an infinite amount of gravitational potential, you would just get a finite gravitational potential from all sides, cancelling each other out. There is no such thing as center of mass. Center of mass is just a tool we use in classical mechanics to simplify equations. But in reality, each and every single one of this matter around our ball has its own mass. There is no center to speak of. But there is the third kind of energy, kinetic energy, which is much harder to justify as a negative. Photons could have negative energy because their energy has different consequences, fine. Gravity has negative energy because its energy has different consequences, but kinetic can't be negative. It doesn't make any sense. This sentence won't stop us though, because we're not here to be reasonable. We're here to do math. So let's see what happens when kinetic energy becomes negative. We'll use two cubes colliding elastically with each other on frictionless surface. And first we should see what happens with normal energy. So, the first cube will have 1 kilogram and will be traveling at 2 meters per second. Second cube will have 3 kilograms and will be traveling at 1 meter per second. What happens when they collide? Well, when they collide, they just start going in opposite directions. Calculating those two new velocities is surprisingly simple if you consider that you need to conserve momentum and kinetic energy, and if we combine these equations we get this, equations for both velocities. There are two ways to get negative kinetic energy, either negative mass or imaginary velocity, and imaginary velocity is similar to imaginary time from the first example, so boring a value that's impossible to visualize. But the second way is possible to visualize, negative mass. So let's go back to our example. Instead of giving our first cube 1 kilogram, let's give it negative 1 kilogram. Now what's really cool is that we can just plug in our new values and get something weird. I mean, makes sense. Right here we have positive masses, so we get a collision. Right here we have negative masses, so the collision is going the other way. But no, something's wrong. I wanted to break physics using math. This isn't good enough. Why isn't negative mass breaking physics further? Well, that's because for each energy we pulled a sleight of hand, and you see we kind of redefined them each time. For the photon, we just said that negative energy can exist because of the wavelength, right? So negative wavelength, which basically means that negative energy has no consequences. For gravity, we said that negative energy can exist because we just care about the difference. Nothing broken there. And for kinetic energy, we said that negative energy can exist because of exotic matter. So matter with negative mass would have negative energy in this case. But hold on, how could we have all of these energies be negative and yet still walk? Well, that's because energies don't really exist. As I mentioned, I did make a video about this, but energies are more of a tool for describing the universe. So redefine the tool and all of a sudden it can be negative. But that's for negative stuff, like exotic matter and negative mass. But let's go one step further. Let's go for imaginary mass. Imaginary mass is way cooler than you think. So far our experience with imaginary numbers has been meh. Imaginary time, can't visualize it. Imaginary velocity, can't visualize it. Imaginary length, we haven't gotten around to actually explaining it, but it's just time dilation for length, so the exact same thing as the first chapter, can't visualize it. But mass is different and way cooler. First, in order to appreciate just how truly amazing it is, we need to ask the question of, why can't things travel faster than light? You may think that the answer would be, well, make it. If you go faster than light, then you end up with imaginary time, imaginary length, and all sorts of unpleasantries. But that's actually not the limit. Yeah, believe it or not, imaginary time is not the thing stopping us from traveling faster than light. What's actually stopping us is the energy. Allow me to introduce you to yet another relativity equation, an equation for the total energy of a particle. As you can see, for low velocities like the ones that happen from our everyday life to space travel, this right here is really close to 1, which means that this equation could be simplified as E equals mc squared, everyone's favorite. However, when we accelerate a particle more and more, the velocity becomes more and more significant, and one thing which you might realize that the higher the velocity, the higher the energy. In other words, here's the energy of a particle at half the speed of light. Here's the energy of a particle at 75% speed of light. And as you can see, the closer you are to the speed of light, the quicker it's going up. And so the more you'd like to accelerate the particle, the more energy you need, to the point where you need an infinite amount of energy to get a particle to the speed of light. But you already know there's an except coming in, right? So what this basically means is that we have this region in between 0 and the speed of light, which are basically the speeds our particles can achieve. But now, let's introduce imaginary mass and see what happens. If we introduce imaginary mass to our standard speeds, we get an imaginary energy, or in other words, add it to the list of things impossible to visualize. If we, however, try imaginary mass with speeds greater than the speed of light, then right here we get a number greater than 0, and so we get an imaginary number, but this time we get in both the numerator and the denominator, which means that we can just cancel them out and we get a real, normal, honest energy. And that's why imaginary mass is really cool. That's because tachyons, hypothetical particles with imaginary mass, not only travel faster than light, but have to travel faster than light. Whilst for our normal particles, the minimum is 0 and maximum is speed of light, for tachyons maximum is still speed of light, but the minimum is infinity. This would also lead to another interesting phenomenon in which you basically be able to send information not only faster than light, but into the past. So basically time travel, this time walking time travel, but that's a story for another time. So the question remains, why is it so hard to visualize any of these variables being broken using math? But mass is so simple. Well, that's because mass is not really what you think it is. So what is mass? Is it the amount of stuff? Is it the weight? Is it the difficulty to accelerate? Is it the interaction of the gravitational field? What is mass? Well, it depends. We generally call mass anything that depends on the amount of matter. Lots of stuff, lot of mass. Strongly attracted by gravity, lot of mass. Difficult to accelerate, lot of mass. Mass is a term we created to help us describe reality. It's an abstract term, which makes it easier for us to calculate things for bigger objects without having to simulate all of the intricate ways in which particles making them up interact. And that's sort of at the core of the big math versus physics problem. It's a common point of discussion to ask if math is created or invented, but it sort of omits the true reason for why math even exists. All of science exists for the sole reason of being useful. The end goal is to describe reality in the most accurate way, and all different fields of science are tasked with creating that description differently. Math is trying to tell us what could be. Physics is trying to tell us what is. That's why when we take what isn't but could be, it breaks physics. Breaking physics in this case shows their discontinuity. Energy, for example, is just a concept. It's something we made up to describe how cubes bumping into each other behave. And since we only needed positive numbers to describe the sort of collision, we never bothered to invent negative ones, so negative energy doesn't really make sense. That all comes from the fact that energy as we know it probably doesn't exist. And to that you might say, make it, how could energy not exist? Of course it exists, we all have these fancy rules about it, but that's not quite the case. What is energy? Well, that question took me 26 minutes to explain last time, and the answer is not as simple as you think. The short answer would be, energy is a tool we use to describe reality, but it doesn't have to be real. This sort of thinking may confuse a lot of people really fast, because how could energy not be real? But we've already been in this place before. When you get introduced to classical mechanics, it makes sense, you know, mass, velocity, distance, time, but what many people will not realize that classical mechanics is an out-of-date theory and generally wrong. It's been replaced by relativity, for example, which we've been using mostly over this video. Relativity, which also doesn't have to be real, it's just the best theory we've got. When our energy is negative, math tells us what could be, but physics tells us that it's not. When our velocity is faster than the speed of light, math tells us where we would go, but physics tells us that we can't. When time is not only negative, but imaginary, math tells us that it could exist, but physics tells us that it doesn't. And that's why breaking physics using math works. Math tells us what could be. Physics is trying to tell us what is, and that's why when what could be collides with what think that is, we break physics using math.